Thank you, everyone. My talk is slightly overlap with Jason. I was his PhD student for 5 years, causing him a lot of trouble. So as you can see, this work involved a lot of people. Okay, and basically, I'm not going to go into the technical detail. Jason already talked it brilliantly, and Yijit and Cheng and Holing already said it. So I'm just going to tell you the story how we go so far. Okay, and some of the progress that we've done, because I know about half, I'm familiar with half of the face in here that has been following our work in the last 3 or 4 years. Okay, now let's start. So today I'm going to talk just a little bit about the background, the research team activities, and some of the future works. So a little bit of background. I stole this from Jason's slide. Okay, so we got a ship that moves on the water with velocity u. It will generate a developing turbulent boundary layer. And from this turbulent boundary layer, we'll have some sort of skin friction drag. About 80 and 90% of the total drag are due to these guys. Okay, and this problem is made worse due to these little guys, the surface roughness, and in the form of biofouling or hull imperfections. So I'm going to talk about those two things. All right? Now, even a recently cleaned ship hull can still create, will have a roughness, unfortunately. Okay, now, Jason said in 1915 something, people start working on it, which is right. So in the last 100 years, there has been so many studies about this, and this is only a quarter of that. I'm showing this so that I can tell Jason that I've done my homework. Okay, so now, basically all of this work in the last 100 years are based on majority, at least in my field, in the turbulent flow field in fluid mechanics, are based on lab experiment, CFD, in situ experiment, and empirical estimation. It's the same that what Yijit and Jason have been talking about. Each of them has their own good things and bad things, okay? And I'm sorry if I'm a bit wrong in here. I'm not a CFD guys. Cheng and Yijit will know more, okay? The thing is, it's difficult to do all things together. You need a lot of people and human resources to do it, and it's very, very, very expensive to do. So that's why normally people only do 1 or 2 of them. Okay, but I don't know what Jason and maybe Jason, Nick, and I have been drinking, and then we talk. Okay, let's do all simultaneously. Why not? Okay, so we decided to invite a lot of our colleagues from the UK, Australia, and Indonesia to work together on this. So it's involved Industry and Classification Bureau. Okay, now the work is pretty much similar like Jason said. We need a holistic approach. So we got a lab, in situ, and also a little bit of analysis together. Okay, and it's involved a lot of money. I can't sleep for a few days when we were first thinking about this. How we do this, but luckily we got a lot of friends together, so we chip in together and we apply funding basically we ask money from 3 countries and they actually say yes, so yay, we can do it. Okay, so and this is just a little bit how we did it so far, just our journey. So in 2015 we approached our colleagues, we applied funding, we got the funding maybe around. The big one is from the British Council. This is about March, and a couple of months later we got the ferry and we can put optical access in the ship. If we consider the 9 years that Jason and I and Nick been talking about, so 6 months is like a magic to us. So we did a few experiments with the clean in the lab. So we did an imprint, we did a lab in experiment, and then after a year, the ship is always docking every year. So after a year, because it was using a really high quality anti-fouling, like Jason said, the hull is still really pristine. So what these guys did is they only put a water just to clean just small slime, and about a week later, we did the LDA experiment inside the institute. Okay? And after that, some of our colleagues in Indonesia decided to make an Indonesian Biofouling Consortium, and last year actually, I met John Alonso and we talked about glow fouling, and just recently we did the foul hull LD experiment, the one that Jason just shown just now. It's still fresh, it's just done on December last year. And we got new friend. I'm having Chang to help me with the CFD studies. So as you can see, the group is getting bigger and bigger. Now, I'm going to talk a little bit about each of this work that we've done. So like I said, just a little bit of overlap with what Jason did. So the first thing that we have a diver. We design an underwater surface scanning. Okay, so basically we work with the diver to design the ergonomic. It's ongoing works. It involves 8 master students. Yeah, it's a lot of people on it. And so basically it's just a simple 3 by 3 camera array looking at stereo. And then we do a reconstruction, just a simple reconstruction. All master students can do this. If you have a student that cannot do this, they do not deserve to pass the fluid mechanics class. So they reconstruct this in a 3D, okay, just using a MATLAB code, okay. It's compulsory. All of Nick and Jason's student has to do this, okay. Now, that's the first part, the monitor of the whole surface state. Second one, we need to combine it with the lab, in the field experiment. So for the field, again, with an LDA, with the LDA experiment, that's my office for about a month, 40 under 45 degree, very humid. I don't know what I did, but yeah, why not? Okay. Now, we did 2 types of experiment. The first one is when the hull is relatively clean, and that's the imprint. And the second one when the hull is very dirty, when it's just about to enter the dry dock. Okay, and this is the result. Jason already shown you. The first one, the CAS is 0.5, and this one is 30. When I first saw this, I didn't believe it. I sent it to Nick. He didn't believe it. He sent it to Professor Mike Schultz. Everyone didn't believe it. Everyone was so surprised. I got so many data. They're all showing the same results. The reason I was surprised, because when I go to this paper by Professor Mike Schultz in 2007, the heavy fouling is 10 mil. And when we look at it, what on earth is that? So it's like 3 times than in the one in the textbooks. So we just very surprised with what we found that. Okay, so while we're doing the field experiment, we also do some lab experiments, because we need to see what happens if we do it on a lab, because this method in a wind tunnel is already well established in the last 100 years. Again, so the experiment that we did is the recently clean hull. Again, we scan it with our laser scanner, the same scanner that Jason been using for his biofouling, and we measure the flow over the surface. Okay. That's inside the wind tunnel. That's a ship hull roughness. Again, to match the Reynolds number, I have to scale the roughness. Okay, because the Reynolds number on a ship is much higher. Okay, now, and again, the sand grain equivalent on the wind tunnel is so it's 100 micron. But when we look at that, why on the field it's like 500 micron, and when we look at it, like, whoa, so many discrepancy. But to my surprise, we got that. Okay, so I'm a turbulent flow. I really did not know anything about shipbuilding. I only entered this field 3 years ago. When we were in the dry dock, I asked those people, so what are you going to do with this? You're going to go up again and go down? They said, no, it's too expensive. So yeah, there's a lot of that on the bottom. So apparently, according to my colleague who is working in the anti-fouling paint, it's quite common in the industry. When we showed this to the people in the Turbulent Flow conference, the horror of Turbulent Flow community was just popped out, and we was just so excited, like, whoa, because for us, this will generate a large-scale vortex flow. I don't want to go there. That's the worst thing in anyone who do vortex flow, I admire you. Okay, and you just right, it's very complex. So from those results, we can do what we call a prediction for a full-scale ship. So right now, I'm just gonna ignore the one on the ship experiment for now, because I found out we got that new horrible counter-rotating vortex. But if we go to the fundamental of the turbulent flow with the lab experiment, we can, by using mean momentum integral, I can predict what happened in a full-scale ship. So this is a ferry at a cruise ship. That's the differences on the CF. At the higher speed, they got a higher drag. Please ignore the red and the blue mean. I'll explain to you what's next. I just want, in the next section, I just want to show you that as with the Reynolds number, you will have a higher drag. Okay, now, this is also reason I have to be very, very careful when I say this. So recently, my colleague Nick Hutchins developed an empirical estimation based on a DNS study. It's a long study. We're using DNS, so it's highly precise. So we can actually estimate the increase of a drag of a turbulent flow from a roughness just by knowing at minimum we need to know average height of Ka and effective slope. Yes, those two values can easily obtain when you have either a laser scan or camera image. It's just a simple 4 lines of code. It's easy. Okay. Now, I tested those. I tested the empirical estimation using a realistic roughness. The first one is a recently cleaned hull. The second one is Jason's fouled hull from his study in 2016. Okay, so if we go back to Mike Schultz's table, okay, so this recently cleaned hull, you got my KS is about 100 microns. You saw it just recently, and Jason's was about 300 something. Okay, and from that, I can do a full scale prediction on an actual ship. That's a smooth wall. The lower one, this one, is the recently cleaned hull. The top one is the fouled hull. Red is the wind tunnel experiment. Blue is the empirical. Not too bad. Like I will calculate about 2 until 3% error. But again, like I said, please be careful with this. Do not trust me, okay? Because we have to be careful with the empirical estimation. So far, I only tested with the 2 surface, realistic surface, and it works not too bad. But our prediction, it may not work really well. It's a really, really heavy fouling. There's still a lot of studies that we need to do. But yeah, you can imagine the last 100 years, the best that we have so far is still here. And now you imagine my horror when I saw that patches, it'll make the calculation more complex, the empirical. So this kind of, I tried it, this kind of biofouling. So I did an imprint, laser scan, tested with the empirical estimation. Nope, it hated. Okay, so you have to be careful with that. So in the last 3 years, we've done a lot of studies on it. So there's a few conference papers that you can have a look, and we have 4 papers that are gonna coming out soon. If you can see, we got so many data that we have to write it one by one, and driving me crazy. I can't sleep at night. The next thing, as you can see, just like what Jason and you said, it has to be holistic. We can't just look at it on one. It's extremely complex problem from the turbulent flow point of view. So that's why we decided to add the computational fluid dynamics to join this big complex party. That's where University of Adelaide coming in. Okay. Apart from the technical progress that we've done so far, I just want to share that for our partner, in the spirit of glow fouling, the one that John Alonso told me, like in 2017, from this joint work, our colleagues in Indonesia has developed like biofouling consortium to start looking at this into whether the country is part of the LPC of biofouling, and they also been advising the Indonesian government, and also from this we can educate 2 master students and 1 PhD students. In fact, one of them will come to our lab and do more work. So the joint research with the developing nation are very rewarding. It took us 10 years. We didn't go anywhere. And then when we approach our colleagues, and then like 6 months, here's your ship. I'm like, wow, okay. For some future works, we're going to do a CFD studies. And this, oh my God, I really hate this. I don't know. You guys in the shipping industry, I don't know. Oh man. So right now, Professor Nick Hutchins has a study, a large study with several PhD students to look into more of this heterogeneity. Okay, it will be a while. Okay, and hopefully we get more studies and it can be put into the empirical estimation. I don't know why I don't know how, but we'll try. That's the best we can do. We'll try. Go back. And we try to improve the estimation and the results to look at fouling that this big. Because so far the one that we've done is only in a small pattern. And this is our ship, and that's the glass. There you go, on the bottom. See that glass? This is when it's just, when we did the experiment just before it goes, that 30 millimeter sand grain roughness, that crazy numbers come from this. Okay? My laser can't reach that. So the next study that we do, luckily we managed to approach another company in Indonesia. The boss told me, yeah, we can borrow you 150 until 200 meter ship. Finger crossed, hopefully in 2 years when I'm coming back here to present to you, we have data from here. Yeah, so John Lewis, yeah, you have to organize again. I'm very sorry about that. I think that's it. And my final takeaway is just if anyone wants to talk about us and have a ship that we can borrow, Jason and I will be more than happy to have a party in your ship and to experiment. Thank you very much.